think the thing that makes us unique as a species is our relationship to our tools. We don't do very well in cold weather or hot weather. We have no fur or hair. We're not particularly strong. We don't know how to hunt. We're not very fast. The thing that makes us unique is that we have these big, glorious brains, and it allows us to manipulate our environment in a way that has not been seen in the history of our planet.
This is Catie Cuan. She's a roboticist and a dancer.
The first time I ever danced with a robot, I felt myself all of a sudden on this long continuum of my species, my ancestors, and our tools. Of some, thousands of years ago, somebody sitting down in front of a fire and feeling the majesty of that moment, the warmth to the wheel and the printing press and the first computer and the internet. And I just felt myself along this long continuum of being in relationship to a machine in a way that allowed me to step outside of my body and be involved in something new. That feeling of I am in relationship to magic, the sensation, that's the experience I look to create.
I love that idea about human beings and our tools. We first started using them more than 2 million years ago. Looking into the future, just think what we could create. You might be thinking, okay, Astro, I get that you're trying to evolve human tools, but why on earth was Catie dancing with a robot? Good question, and I'll tell you why. Because it's not just about making tools that are more efficient and powerful. To really create breakthrough technologies that can help us with complex tasks and actually enhance our lives, it's about understanding humans better so that the tools can really help us, even with all our nuanced needs and in our most vulnerable moments.
My mother, towards the end of her life, she wouldn't even say hello when I called her. She would just say, "When are the robots coming?" And we would have a little routine almost. And I'd say, "Well, it'll be a little while, Mom." And then she would say, "Well, they better come soon."
This is Hans Peter Bronmo, HP for short, a talented technology entrepreneur with a background in computer science. And as a son, he was desperate to help his mom.
So she had pretty advanced stage Parkinson's at the end of her life and several other, ailments. And she had 3 people every day coming to her house. And it was a rotating cast of characters, most of whom she had never met and would never see again. And they would show up and do really, at times, tasks that I think felt like they intruded on her dignity. She would lose something on the floor and she couldn't pick it up. She would shuffle her feet and the carpet would move over, and it became a danger for her that she might trip on it later and fall. And these are little things the robots could help with. And then she loved playing cards. And imagine if one of these people came over and had the time to actually play cards with her, because the robots had dealt with a lot of the little stuff. I realized so many of these examples would have helped my mom.
At X, we focus on tackling the world's hardest problems with radical ideas and breakthrough technologies. And that was the goal of this moonshot, everyday robots. Could we create a better kind of robot that could really help us in these types of situations, but in a way that we actually all want to be around? And here's the next question. How might dancing with these robots help? This is the Moonshot Podcast. I'm your host and captain of Moonshots, Astro Teller. In this series, we're taking you behind the scenes of X, Alphabet's Moonshot Factory, to tell the inside stories of our biggest, boldest ideas, their successes, and yes, their failures too. And in this episode, we're going to explore 2 projects focused on the fascinating and complex world of robotics, which we believe are some of the next generation tools that are going to inhabit this future we're building and work alongside us. Okay, let's get back to HP, who was telling us about his mother. She was getting older and needed more help, but the big problem is she wasn't the only one.
Populations are aging and already in many countries shrinking. The replacement rate of 2.1 child per couple is dropping below 2.1. So that means that we're going to have more old people and people live longer. So you get an aging population. So the people that are actually here to do the work won't be here anymore. And just to throw some numbers at this, China today is at 1.3 billion people. The predictions are that by the end of this century, they're going to be at 730 million. So half the size.
And like 40% of them will be over 65 at that point.
So the actual people in the workforce is shrinking significantly. So from my perspective, once I really started drilling into these fundamental challenges, I realized that the robots can't come fast enough. We really need robots if we want to continue to live not just as good as we've lived, but also sustainably as good as we've lived. Robots are going to be a huge help in terms of maintaining infrastructure, whether that's for productivity, it's for longevity, it's for quality of life. So this isn't like nice to have. This is really a necessity for humanity to solve this problem. And then the fundamental question is, how do we solve it, and who solves it, and how do we solve it to our general benefit?
That was the key mission of our moonshot, Everyday Robots. How do we create robots that behave in harmony with humans and in a way that is actually scalable? Now, I'd been wanting to get Hans-Peter to work at X for a while, and I had a sneaking suspicion this project would be up his alley. So back in 2015, I pinged him an email.
And it was cryptic. It just said, "Do you like robots?" And when Astro Teller asked me if I liked robots, and I actually showed up at MIT as an undergrad off the plane from northern Norway, carrying a little orange robot under my arm.
HP had actually built this little robot in the 80s while he was doing his Norwegian military service. While his fellow servicemen were playing cards and relaxing after a long day patrolling the border in freezing temperatures north of the Arctic Circle, HP was trying to build a robot, with mixed success.
And so, yes, I liked robots, but I'd always seen them as these sort of big, dumb, and dangerous machines that it just wasn't the kind of robot I wanted to build. So, of course, I said, well, let's talk. And I think I had, when I counted them up in the end, I think I had 27 interviews.
I hope he's exaggerating. But yes, we do try to be thorough in our interviewing at X. What we're trying to do is hard, and it isn't for everyone. So checking carefully for a match is worth the effort. But anyway, HP was in, and he set about designing this moonshot, which wasn't just about pushing tech frontiers to make the most capable and useful robot possible. It was about making a robot that had humanity and society's needs reflected in its core. Time and again, in the public imagination, the idea of robots is seen as threatening, but HP wanted this time to be different. And to achieve that, he needed to recruit a team with a wide range of perspectives.
So often, people who worked on workers' rights, people who are philosophers and thinkers about the future of humanity, these people are in an adversarial situation. And I sort of figure that, well, we can have conversations with them now before this stuff is baked, before it's actually finished, and we will learn. And so we created something that we ultimately called Impact Lab. We had a really interesting cast of characters. We had a philosopher in residence. We had a labor leader, Andy Stern, who was former head of the SEIU, second largest labor union in the country, advising us. And we would have these really interesting convenings and conversations internally with them. And when we invited them in, they weren't concerned. They were curious. They were very collaborative. And we ended up having conversation and having dialogue. There was a point where I said, we should have an artist in here, an artist in residency.
And that's where Catie Cuan came in. She used to dance with the Metropolitan Ballet, and this unusual combination of experience made her perfectly suited to Everyday Robots' goal.
We're going to see billions of robots in our lifetimes. I fundamentally believe that.
I agree.
We think about what are the technologies that are most likely to show up in the next 50 years. For me, I strongly believe it's robots.
But you're probably still wondering exactly what dance has to do with robots.
When I think about robot choreography, what I do and a few other people do right now is fairly novel, but there will be tens of thousands of people who do what I do in the future. Everything, for the most part, that moves autonomously is a part of nature. Squirrels, trees in the wind, all of a sudden a baby or toddler, probably more likely, wiggles by you. And we have developed over hundreds of thousands of years in evolutionary prior to comprehend what that motion means, whether or not it's threatening. Now, all of a sudden, we have things that are moving autonomously, like Waymos, like robots, that are not a part of nature. And our brains have not adapted over hundreds of thousands of years of observing and experiencing that motion to understand what it means. I firmly believe that if we don't land that robots move in ways that are non-robotic / friendly to humans, we miss what is a very small window for these machines to be seen as not only more friendly, but also safe. And when you think about having a robot inside of a place where people are especially very vulnerable, whether that's a nursing home or preschool, safety is not just important, it's the perception of safety. It's the perception of care, of closeness. And I think choreography will be the unique unlock that will get us there.
Can you give an example or two about how this kind of body language could play out either badly or well, depending on relatively small changes? So we're imagining a robot and it's coming over. I don't know, it's going to open a door, it's going to pick up a cup. How would it be done so that it feels threatening or confusing? And what's the good version of that?
Give you a really simple example. You're walking down a hallway and there's a robot that's walking towards you. There are some versions of today's robots that will get very close to you, because that's how long it'll take for the robot to detect where you are, very close to you, stop, and then somehow orient around you. That's not what humans do when we pass each other, right? We see someone at a specific distance. The two of you anticipate that you're going to be changing lanes effectively, and you adjust your bearing well before you arrive right in that human being space. And it's so subtle, but these kinds of proximate things, they either freak you out and make you think this robot's going to run into me, or they create just enough uncertainty that you don't know what the robot's thinking. How strange would it be if you were crossing a hallway next to a person? They walked all the way straight up to you, right in front of Astro, and you were like, what's going on here? Are they going left? Are they going right? So there's something like that about being able to change orientation in space that's very subtle. And I think those kinds of subtleties, those are the kinds of choices we need to make with robots.
It's qualities of our movements that we'd never even think about as humans, but are key to creating a robot that feels friendly and helpful rather than creepy. But of course, getting a robot to behave in a humanistic, well-choreographed way is much easier said than done. The team got to work, and one of the first big debates was what the robots should look like.
If you go too far and you make it too human-like, you can really creep people out. And if you don't go far enough, then people aren't exactly sure how to relate to it. And so there's so many factors like this at play when it comes to human-robot interaction. My feeling about robots is that they should look like robots, but that there's a fair amount of research out there that things that are beautiful make people calmer. They actually make you more productive. So I think being around a robot that's beautiful and ethereal could be potentially beneficial for your health. But even more than that, my feeling is that we get to build the future that we want. We make choices about what that future looks like. And we can choose things that are beautiful, fascinating, I am compelled to want to be around, or we can choose to build things that are scary, alienating, annoying, boring. And if we don't make conscientious decisions about those things, we don't get to complain. We don't get to sit there in the future and be like, oh, I wish I wasn't surrounded by all these ugly, scary robots. It's like, yeah, because that is the choice that we make now, today.
Now, exactly how human robots should look is still a hot debate among roboticists, but HP agreed.
I didn't want these robots to look like humans. I also forbade the team from putting screens on them. I don't want to poke at the robot and cheat by having screens. And so we had some design principles early on that were kind of baked in. So the ultimate robot we built had wheels. It was on a little base. In that base was the brain, meaning that big computer and a few other computers, big battery. Then it had a long stem. And on top of the stem, there was and I use, Austin Powers quotes here, a head. And then there was one arm and wheels as opposed to legs.
Yeah, I remember you and I had all of these frustrating moments trying to talk with roboticists who really believed in legs.
Yeah.
And I know for myself and for you, we were very much aligned. If you can be awesome on the first floor and our only problem left is that we can't get to the second floor, we'll get legs for the robots. But since there's no evidence that we're awesome on the first floor yet, let's not worry about legs for right now.
I know. It's and there were so many people working on legs out there that I figured that's kind of just a replacement strategy. What's the hard problem? The hard problem is figuring out how to move around and not bump into things. But the other thing is they are highly power inefficient. I like to say, Before cars, we had horses. We didn't end up giving cars 4 legs, right? Although horses are really good at what they do, cars are much more efficient.
So now you know what the robots look like. Let's get to the heart of this moonshot. How were HP and his team going to create helpful robots that interact harmoniously with humans? Not only that, but how would they do it in a way that could easily be scaled up to actually make a difference in the world? First, the team looked at the core skills the robots would need.
We started just breaking it apart. We need robust navigation. We need robust perception. We need robust manipulation. And I think this was one of, the insights you really hammered in early on, is the only way we're going to make these breakthroughs is by using artificial intelligence and machine learning. And this was, early 2016, right? So nobody was talking about LLMs yet. In fact, the transformer technology behind large language models was just being invented at the time.
Over at Google Brain.
At Google Brain, exactly. And so we were taking these nascent technologies and saying, in sort of that good old X fashion, right? Is there a technology here that if it happens in the future, this will create some disruptive, like non-linear break in the development curve? And then we looked back at robotics and all the stuff that's been going on for years and even decades. And we looked at why didn't they work? Ultimately, they weren't robust to all of the messiness, as we like to call it, or all of the variability in these environments that we live in, humans.
How to make robots that can cope with all that messy unpredictability of life. It's a huge challenge, and with robotics, programming movements that are simple to you and I can be extremely difficult and time-consuming. So, one of the fundamental principles of everyday robots was that these robots wouldn't be programmed. If that was possible to do effectively, it would already have been done. No, these robots were going to learn by doing, by playing, by trying and failing, with machine learning. And so, we had robots trying to clean up the office, trying to pour drinks, even trying to shave the beard off of one of our engineers.
The play and explore part was so important because this was nascent, and we would discover things. We would discover limitations. We would laugh a lot. But it allowed the team to also motivate each other through that excitement and then start asking themselves, well, how do we generalize something like this? And is there feedback when it pushes the razor against his face?
It was really exciting technology for the team to experiment with. And through all of this play, the robots were getting smarter. And then they built a tool to supercharge that process of play, failure, and learning.
We built a giant simulation. And we ran this simulation in the cloud. Think of it almost like a video game where the robots got to play all the time. And they were simulated, but there was some physics in the simulation. So if they contacted something, they knew what the forces were. There was obviously a visual world, so they could look around and see things. They could move in the simulator. Again, if they bumped into a wall, they would notice it. I think our last year of the project in 2022, we ran something like 240 million robot instances in this cloud simulator. 240 million robots over the course of a year.
So this is robots learning to pick up a cup or a banana,
exactly.
Learning how to move through our building, actually modeled in this video game in so much detail that they could go swerve around people or desks or whatever and get good at doing this.
So I like to think of it as they were at night, they were dreaming in this model. They were sitting there having these experiences like plugged into the matrix. And then they would wake up in the morning. We'd download the model as it had been developing overnight with tens of thousands of robots, practicing something. And because it was a simulated environment, if they did a mistake, the program would know they made a mistake, so we could get feedback to the model. So these hundreds of millions of robots over the course of a year created all this training information and data.
That was the robot's first brain, this giant computer brain in the cloud. And it was the first of 3 brains.
I called it the learning brain. It's where all the models were developed. And also, it kind of had infinite memory, right? So it remembered everything it had done in the past.
It was also a shared brain.
Exactly. If one robot learned something, they all learned it. And then that got pushed back into the robots. So then there was the on-robot brain. And that was sort of the action brain. It knew how to take a picture it saw, basically what came in through its cameras. It had a little LiDAR, those little spinning things you see on the Waymo cars, which are for safety and for basically distance measurements, so they could see things at a distance and understand how far away they were. It would use that incoming data to basically make inferences about what it should do. So you had the on-robot brain that could act. You had the in-cloud brain that could learn. So what's missing? What's missing is what it didn't know, exceptions. And that requires a human brain.
So this is like phone a friend for support.
Exactly.
Like if you're
it's ET call home, right? It's basically, it gets confused, it gets stuck, and then a human needs to come in and say, oh, look to your right, that's what needs to be fixed, or back up 3 feet and you'll be fine. So you needed this human brain in the loop, but you couldn't have one person per robot. You needed it to be extremely efficient. So what I wanted was, I wanted the robots to get to a place where they knew they'd screwed up. So an example would be, I dropped the cup. Like, how does a robot know that it dropped the cup? And then to pull in a person for what might even just be milliseconds to understand the situation, see what's going on, and then just identify the mistake. Give it a hint. And I even wanted that hint to happen with voice. I didn't want you to still sit there clicking. So a human should be able to sit far away and say, oh, just pick up that the cup with the green stripe on your right, and then leave. And at this point, the robot goes, oh, pick up cup, right, looks down, sees cup, picks up cup, puts it back where it's supposed to go, and then maybe calls back and says, is that good? And the person says, thumbs up. And guess what we just did? We also just created some training data that the robot can use to be smarter and smarter.
This third brain, a human brain, connects back to the robot via a large language model. This LLM enables the robot to understand that quick verbal hint from the human and act on it. And this was so much more efficient. Imagine having to program a robot for every exception, every potential error it could make as it navigates the complexity of our environment. Basically impossible. But using Google Brain's early work on large language models, which you can hear all about in episode 3, by the way, the robot could translate unstructured human speech back into structured guidance so that it knew what to do and in seconds go back to autonomous mode. And as the robots roamed around our buildings, there were some OMG moments where we realized that our approach of using AI to teach them rather than program them was really working. I remember one that stood out clearly for me.
When the robots learned to plug themselves in or unplug themselves so that they could go about their days, they were pretty slow at plugging themselves in or unplugging, but watching it feed itself, literally plug in and unplug so that it could sort of go start roaming around the building and being useful. I got chills the first time I saw that.
Yeah.
Tell me one or two things that really hit you like that.
You know, I was sitting in my office one day. This was not too long in. And the robot comes by and I look at it. Just as I do that, it turns its head and it looks at me. But not only looks, but as it travels past, it turns its head, kind of tracks me, and then looks forward again and goes. My heart skipped a beat. It was like, it saw me. I feel seen. It is this fundamental human need to just feel seen, right?
I remember later, you all as a team built on that moment of being seen by giving it the head nod, so that when it made eye contact with you, when it saw you and it knew that you saw it, it would raise its head and then quickly lower it. Just a little like, hey, what's up kind of head nod that really accentuated that I see you moment.
Yeah. Yeah. It would turn its head towards you and then give you that little nod when it detected you and then keep going.
At one point early on in the project, we had what we called an arm farm. It was a long row of robot arms, and next to each one was a box of about 30 little bricks and toys, which the robots would try to pick things out of with its one arm and gripper fingers. Using its camera plus reinforcement learning, each robot would learn whether it had successfully picked something up or not, and then it would share that learning with all the other robots in the farm.
So initially, when it started grasping, it had a 7% success rate.
Yep, you heard that right, just 7%.
By the time we ran this project for, I think the initial cycle on it was 3 months, 6 months, we had gotten up to about 70%. Then one day, one of the engineers comes into my office. He says, you got to see this. And he shows me this video. The robot comes down and it wants to grab this yellow brick. But instead of just like reaching down and trying to grab it, basically shuffled a couple of pieces out of the way, and then it moved over, picked up the object successfully. And I look at this and I said, did we program it to do that? And he just shakes his head. He says, no. And that was when I was like, okay, now we're onto something. This shit's actually working.
Soon, the robots passed a 90% success rate. So Hans-Peter and his team realized they could fix a real problem in the Google buildings, sorting all the trash. If things aren't put in the right bin, stuff that should get recycled or composted doesn't, and we get a fine.
The robot would roll up to these bins every so often and just look at the trash and then learn through experience, classify them, and then drop them in the right place.
Eventually, there were about 180 robots roaming around Google's buildings, cleaning tables, sorting trash, and generally making themselves useful. They were getting smarter with each bit of learning, and they were responding to humans in a way that made them more likable, like giving us a nod when they saw us. But of course, there's much more to human interaction than just the visuals. We get a lot of information about what's happening around us from sound, and that's where Catie and her teammates come in again.
Music mode is where we transform all of the motion from the robots into sound so that the robots play music while they move. So we actually tried a bunch of different soundscapes to see what would work, or work in the sense that it would create a sense of calm and inspiration, an ease, and maybe a curiosity for you to see the robot in a different way. So we played around with heightening the robot's existing sounds, and then we settled on these beautiful instruments in an orchestra. We had a cello sound, we had these beautiful, bass notes, kind of fluttering trumpet sounds. And we had each joint of the robot be mapped to a different sound, and the relative proportion of that joint also was associated with the correct sound. So the gripper is very small. When it opens and closes, you hear this beautiful bell chiming, versus the torso that's a little bit larger, and you got to hear a deeper, more robust cello noise. The experience that people had with the software completely blew my mind. And I would get these emails from engineers who were like, I'm crying at my desk because I've never seen a piece of technology be so beautiful and make me feel so affected. And when we had music mode and we put it on all of the robots, we could turn it on at any time. So you would have a robot that was either navigating down a hallway or wiping a table or sorting trash, and you would hear the symphony of what that motion was manifesting.
Yeah, I don't know if either of these was on purpose, but I felt like I had gotten to the place where I could close my eyes and almost envision its physicality just by listening to it. I could certainly tell how much it was moving and maybe what parts of it were moving. The other experience I had was I caught myself a few times being sad and a little bit jealous that I couldn't make music when I moved.
Yeah.
I felt like it was one of the things where like they somehow had gotten a better deal than us because it just seemed so wonderful. So it felt almost more human.
I think everyone really loved the software. And we wound up running a research study on that project and found that people perceived the robots to be more animate, anthropomorphic, likable, intelligent, and safe if it was playing music mode. And that they also found it meaningful that it was indeed mapped to something real as opposed to here's random music playing, because they saw the robots as more capable when it was doing the mapping than when it was just random sound.
So you very quickly start to turn the sound into a kind of body language.
Exactly right. Yes. And we need those kinds of cues because you probably won't have a robot in the future narrate every single thing it does. It's not going to say, now my front wheels are driving, or
its intentions,
right,
or its needs.
Right. It might not say all of those things explicitly through language. So how can it develop some kind of social cue proxy that is not pure English, but also potentially not pure human body language, the same way that we can point to other technologies and say that they've drawn out their own lexicon simply by existing.
So that's one of the ways the robots implicitly communicated with us in a more appealing way. But what about how they navigated space around humans? Catie had an idea to make it feel more beautiful and harmonious.
what would it be like if you could teach robots how to flock together in groups like animals and do it in a way that they can be in situ with people? So you get this experience of, I'm in the future where there's all these robots around, and yet somehow I feel safe and my motion is legible to them and I can control them with very little training. It was super hard. To my knowledge, no one had ever done a multi-robot project with those robots. And so we wound up learning, using an imitation learning problem structure, all of the different weights of these different aspects of the flock, which created these interesting patterns. And then we also learned the preferences of a choreographer. So me as a choreographer, I would say, let's flock in this way, and then this one, and then this one, and then this one, because I was intuiting what would look the most interesting. We had people say things like, I'm in heaven. Have I ascended to another world? I don't feel that I'm living in the present right now. I feel that I'm in the future. I think so many impressive things that have to do with robotics and technology is about highlighting what the machine is capable of. Look how quickly we can fold these T-shirts. Look how efficiently we can solder these welds. But this was reaching something a little different for people.
I agree. You actually said that part of the goal was to have the humans be able to control the flock. I'm not sure if this was intended or not, but I didn't feel like I was controlling them. I felt much more like I was being included.
Wow. Did it raise any questions for you about what your future life would look like?
Not really, but I might be the wrong person to ask. I live in the future.
Now, I might live in the future and feel at ease with robots, but some people are understandably wary of this prospect, regardless of how useful the right robots could be for society. Perhaps it's not surprising when decades of science fiction have implanted ideas about hostile, dangerous, or violent automatons. And addressing these concerns is perhaps the greatest challenge HP and his team faced.
I've come to the realization that we are highly motivated by fear. We're driven by fear.
Massively.
Right? Fear of change more than perhaps anything. And if we're getting into this territory of not just computers that can think better than us, ultimately, or faster, as we're seeing with artificial intelligence today, but then also transferring that into the physical world and giving it physical bodies. And there's so many stories, so much narrative we can create around that, which is fear-based. It's so easy, right? It plays on our fundamental sort of, protections of like, I need to protect myself. And it sells, right? Like, would you go see a movie about a robot that cleans the table? Like, it's like, that's not exactly an exciting story in terms of its narrative and emotional impact, although it's very exciting in terms of what's going on in the world and how we need help. A robot like Terminator, on the other hand, that comes in to, kill somebody and change the future, well, hey, that's an exciting story. That gets my adrenaline flowing. So we've been used to seeing, and we've been programmed for fear. I'm a techno-optimist. I think that most of these technologies will be helpful. I think that they're not optional. We need to do this. And, we need to be careful because there are consequences, but they will be greatly, in my view, outweighed by the positive effects of it.
There's an economic fear too, of course.
Automation is a fact of human work life. We are always in a cyclical pattern of moving into new kinds of work. We didn't have software engineers in the 1930s. Now we have millions of them. There are always new domains and forms of expertise that are showing up. For example, at Everyday Robots, we had robot veterinarians. It's hard to be a robot veterinarian if you don't have a robot. It's hard to be a mechanic if you've never invented a car. So these new technologies also enable new kinds of work. And I think it's the narrative, not the actual number of jobs that are changing, but it's the story that we tell that is so scary for people about that.
Everyday Robots brought in a lot of advisors to work on these crucial issues around the impact of robots on society and jobs. One of them was James Manica. He's SVP of Research, Technology, and Society at Google, which basically means he's focused on how new technologies can be developed responsibly to humanity's greatest benefit.
Most of the research suggests that, in fact, robotics and AI and machines are going to be augmentative rather than displacing. So the International Labour Organization published this extraordinary report last year after having looked at, I think, something like 140 countries, looking at something like over 400 occupations. And they concluded that the augmentation effect was going to be 6 times the displacement effect. So that tells me that, sure, while of course there'll be some occupations where we'll see the jobs decline, the bigger effect, at least by their measure, 6 times the effect, is going to be this augmentation effect of workers and people working alongside and enabled by these technologies and robotics and machines. And I think that's exciting. That's not to say, everything is solved, Astro. There are some deeper questions to think about the meaning of work and life and how we live alongside these machines, even if they don't fully replace us. How do we find joy, motivation, and meaning in work and in life? And I think those are adjustments we're going to need to keep thinking through.
When you go now to the Google Robotics team, which includes much of the hardware and software and people from Everyday Robots, what are the sort of ideas or thoughts or suggestions you take to them about how they can try to ensure that this sort of turns out as positive as you've just described?
I think one of those ways is to think about the kinds of things that are outside of the range of what we humans can do, right? Machines that can see around corners, machines that can manipulate objects in ways that humans can't. I think the more we can think about those kind of goals and ambitions that go beyond, what humans can do, then we're more likely to be able to build, if you like, augmentative and assistive technologies that enhance what humans do as opposed to replace them.
HP's team had pushed the frontiers of robotics, pioneering the use of AI to scalably train robots to act more intelligently and intuitively around humans. But it was going to require an enormous investment and a long, uncertain timeline to get to a profitable product. So after a number of years collaborating with robotics teams at Google, in 2023, the Everyday Robots technology was merged with DeepMind's robotics efforts, where the research, learning, and path towards a product continues. But at the same time as AI was transforming the way we could create robots to help people with everyday tasks, it was also transforming their potential to help on a bigger scale, enabling the machines that power industry.
We really noticed a big step change in how people felt about automation and robotics after COVID.
I want you to meet Wendy Tan White. She's the CEO of Intrinsic.
We fly raw materials to China because the labor is cheaper there in order to make things. Then we fly it all the way back again. That broke in COVID because the people weren't available, the transport wasn't available. The cost of that is huge. We also realized that the skilled labor understand these manufacturing processes retired through COVID, and the younger folk don't want to go into factories to do these jobs. I remember being in a factory, and the general manager of that factory was explaining to me, we were watching a guy clipping an ABS braking system, flexible hoses into a car, and he was doing it every 5 minutes. And she actually admitted to me that that type of job will actually permanently hurt his back over time. And these types of jobs should not be done by human beings. But nobody else can do it right now. So what I would say is, I think there's been a massive shift to we need that labor. We need to not be shipping things around the world and, creating pollution. We want to bring things like manufacturing back to places in the US, in Europe, etc., such that those jobs will be available here. So I think things have changed significantly in the attitude of the world that we may actually need this.
This moonshot is about revolutionizing the way we make things.
How do robots more effectively make things in the world that are useful and do it in a way that's much more efficient? It's a hard problem to solve. Robotics, by their physical nature, have to be traditionally programmatically exactly told in coordinate by coordinate what to do. It takes a long time to program it. And the question was, could we help those robots do things in a more flexible way?
Here's the thing. Traditionally, for industrial robots, you have to do this programming for every different element of every task in every different factory context. You can't expect a robot that's been programmed to screw a cap onto a plastic bottle to suddenly be able to push a different cap to pop onto the bottle instead. So here's Intrinsic's Moonshot. Instead of it taking hundreds, even thousands of hours to program a robot, could we make that process 100 times easier and more efficient? Just tell the robot what you want and let it figure out the details of how to do it. It's a goal that could transform factories around the world and drive massive economic growth. First things first, let's get to know Wendy a little bit more. She's a leading technology entrepreneur who founded her first company at age just 28. It was called Moonfruit, and it was the first ever cloud-based website builder. At the time, the ability for anybody to create and launch their websites without significant tech background was revolutionary. So perhaps it follows that Wendy's interest in computer science started at a very early age.
My dad was an electrical engineer. So my first memory was he used to take me into his lab. I was about 4 or 5. I used to play with his punch cards, actually, because in those days there was no coding as such. It was punch cards.
For the young listeners, punch cards were thick pieces of paper you'd punch holes into to represent commands or data for computers.
Early programming was coming, and it would take ages. Like if you wanted to code anything now, I mean, forget, code with AI. You were literally having to punch your punch cards with an algorithm and then run it through a machine. If you made a mistake, you'd have to do it again, right? So it's very slow. But I was also fascinated by that.
And the computer science bug also reached Wendy's mom, who was working as a midwife.
My mum actually wasn't allowed to go to college because she was one of 8 girls in Malaysia. And the 2 boys got sent to university, but she got a sort of one-way ticket to do midwifery in the UK, which she was great at. But she really wanted to go back and do a degree. So she did an open university course in maths, then went back and did a degree in computer science while I was around 5 or 6. So she then also was really into it. But she used to miss a night a week out at sleeping to look after me, but then still do her degree.
So with these 2 for parents, perhaps it's not surprising that young Wendy would also get hooked.
I actually learnt to code first on a mail order programming course where I would write my code out on a graph paper, send it by post, because there's no internet, remember? Send it by post to a lecturer who would mark it for me and send it back. So that's how I learnt to code. And I kind of fell in love with it, really, to be honest, from there.
Fast forward a few years, and Wendy found herself in a factory in England's car-making region. And that's where she first saw the problem that has fascinated her ever since.
I was sponsored by Ford Motor Company through college to do computer science. And so every summer I would go to the factories in Brentwood or Dagenham and literally see these robot lines producing cars. The thing about a traditional robotics line, which hasn't actually changed a lot in the sort of 25 years since I was an intern there, is that it's very rigid and fixed. So you effectively set up a line, and it's so hard to program, change the hardware, change the integration of that line, that you have to produce, hundreds of thousands, if not millions of cars to make it worthwhile and make money. And it's very hard to change it, and it's expensive.
But why?
Because every single task has to be built in a customized way. So, for example, let's say screwing a bolt onto a car frame. Those tasks are all very customized and specific to a particular angle of that screw, position of that screw. If it's an assembly line, it's moving every couple of seconds along a line. And so it's very fixed, this process.
You mean kind of like if the bolt moved over by 1 millimeter, the whole line would shut down?
It would literally shut down. It hasn't got the ability or flexibility to adapt. If you actually had human beings doing it, for example, let's say when we put a key in the lock or a screw in a hole, let's say, we use vision first to see approximately where that hole is and how to get the screw there. We use feel to then move that screw in once we're vision there. And then we use a lot of force torque to turn it. Yeah? All those things have to be done to, and more intelligently be adaptive in making or building anything. You would have to add vision, touch, feel,
sound,
force,
maybe.
Sound. All the senses, actually, that we take for granted, you actually have to add that into a robot line. And I think that's the breakthrough that Intrinsic really looked at, was how do you add all that sensory input, but also output? How do we do all of that combined such that we can make the process adaptive rather than very fixed and therefore very expensive?
Paint the moonshot for me for a second. 10, 15 years from now, Intrinsic is wildly successful. It's changed the world. Like, what happened? Like, what did it do?
Imagine the factory of the future, where rather than these fixed lines, every task can be done in a modular way, right? We as humans, we are task machines, but we're like Swiss Army knives, right? We can do multiple tasks. Like I can screw, I can fix, I can weld, I can stamp, I can bend. Robots can't fully do that today. If they could, if a unit of a factory could do multiple tasks, suddenly you get flexibility. So what we're imagining is a future where this factory has a modular setup of units that can do different tasks, that can also then be reconfigured almost in real time. Rather than, as I said, you need these big lines to do hundreds and thousands of products, you could actually have a small unit of those that could produce 3 things because they can adapt to what the 3 things is you want to build.
So these robotic units or cells are little groups of robots working together on one stage of the assembly process, and they can be easily adapted to whatever different processes the factory needs. And the vision for this was to build this with software, enabling others to create their own robotic work cells, kind of in a similar way to Wendy's first business, the website publishing tool.
Could we make effectively building a robotics application as easy as it is to publish online? And that effectively democratize the access to robotics. Why do you want to democratize access to robotics? Because we want to unlock the value of making and producing for many more people, right? So what we really looked at doing was, can we make it almost like an Android of robotics, where there was almost a general usable interface to build any application that didn't care about the type of robot, the form factor of the robot, the programming of the robot, the controller, the hardware setup. So you could literally just almost design it in simulation and then get that task done for you, right?
One of the ways that I imagine the very long version, I mean, it's a little tongue-in-cheek, but I imagine a bunch of robots kind of kicking back against like the sidewall of a big manufacturing environment. They're kind of vaping, drinking a beer, waiting for their next like assignment. And someone shows up with a complex CAD file and says, make this for me. Make it fast, make it cheap, make it very reliable so that it turns out right every time. And the robots say, no problem, we got it. They can just look at that CAD file and understand exactly what it is that's supposed to be made and how to make it. And they all just like scurry, they get into like little scrums, and they just start ad hoc making it for you. Like, is that crazy? Could we be there in 10 or 15 years, maybe without the vaping or the beer?
Yeah, I don't know if they need to vape or beer. They might. You know, if intelligence goes the way we think, they're going to have different personalities. But anyway, to be honest, I don't think it's even 10 or 15. We are already able to take a CAD file and actually start to make an object based on that design.
A CAD file is a digital file that holds all the technical data for any 3D design. And this tool that Wendy's talking about is called FlowState. It's an application builder created by her team at Intrinsic that allows you to design a robotics application that can perform a multitude of tasks: drilling, bending, screwing, welding, polishing, using a simple user interface. Not only that, it can actually build that robotics application onto the robot for you. Here's an example.
One of the FlowState customers wants to build an application to bend metal brackets, and many of them but different sizes and shapes. So usually you would have to either have a human do that, or you'd have to program for hundreds of thousands of hours different robots to do that with many different software packages. Take a long time. FlowState's like a one-stop shop. Yeah, you can go in, design the robotic cell that can do this bending. It's visual, so you can literally see a simulated version of the robots.
Almost like you're in a video game.
Like you're in a video game. It's literally drag and drop. So you can go, okay, I've got this type of robot. Oh yeah, here's a little picture of the robot. I can drop it into my cell, which you can see visually on a screen. You can assemble it. You can put it together in the structure you want. It will also help you. It will tell you, oh, that doesn't work physically. It'll help you learn that it's not going to work in the real world, basically. So in a way, what happens is it creates a simulation and a belief world of what that cell looks like. And then the other thing you can do is you can visually create a process. So let's say you want the process to be, I want to pick this weird shaped piece of metal up that looks like this and bend it like this and then put it in this box over here. You can actually describe that process through a graphical user interface too.
It looks a little bit like a flow chart.
Like a flow chart, and we give you a library of different skills that you can put together. So the idea is more like Lego in that rather than you having to program every single task, you could assemble a set of skills together, like sort this pile, pick up this object, screw it together with this one, insert this over here, and then drop it back in this box over here.
So the key is the robots you're building do all of this trial and error in a simulated software environment. Then you deploy it onto real hardware and adjust the process as necessary. And here's the game changer. This library of skills can just be applied to the robots so you don't have to code them yourself. And the part I think is especially cool is that any developer can get involved by adding skills to that library and eventually getting paid by others for those skills they've made for the robots.
That opens up an opportunity to share the value of the design, the inherent programming that's happened underneath from a developer or a designer, and actually share that with another end user who's prepared to pay for that, because they want that too. And then reapply it to whatever hardware they've got, so it's hardware agnostic. That really creates flexibility, opportunity, lower cost. And we found that people would like to share that in a marketplace. This is actually already happening.
Flow state can be used to design and build any robotics application for any manufacturer, which really makes it accessible and scalable.
We are more like the Android of robotics than the Apple iOS, right, of robotics. In iOS, you use the Apple hardware and stack, which is great. It's very vertically integrated. There's probably an assurance it works a certain way. In the Android of robotics, the design is open such that many different manufacturers can work using Android. So for me, that was always more democratic and open.
This ability to quickly and flexibly create robotic work cells for making things could transform multiple industries. And flow state is already out there, being used by some of the world's biggest companies, enabling them to change production processes or scale them up and down quickly and easily. But this isn't just about the manufacturing industry. The impact could be far bigger.
The reason we started with industrials is because industrial are already using robots to make things. There's data there, there's products they're building. The real vision we'd love to have, we'd love it that just your average Joe could actually have something made for them automatically in their home. And so what is the most assembled furniture in the world right now that everybody knows about? It's probably IKEA furniture. Most students now will start by trying to assemble a flat pack bookshelf, right, or a chair or something. And so we actually started working with IKEA almost like on a prototype discovery phase, which is, could we get our robots to take something as mundane but commonly bought like a bookshelf and do that? And it was hard, right, to start with. Most of you who've ever built an IKEA piece of furniture know how hard that is, right? Even when you've got the rubric, the design, the instructions, getting the pegs to line up, getting the screws to line up.
I've been brought to tears by IKEA furniture.
I think that's right. You suddenly really appreciate that if you get the screw in slightly the wrong position, it doesn't fit together. It's wobbly. You're sitting on a part you didn't realize, right? You argue with your partner. But can you imagine if actually you just had a little robot unit at home that did it for you, right? The pack was shipped to you, dropped off to you, and there it was, and the robot unit just sorted it out. It's a very different world. And actually, it's also one that's less wasteful. You don't have to have everything made and built already. And this is actually the thing even the big manufacturers want. They would love it that they could just build you a customized one-off item for you and not have had to build 100,000 of those just in case, because it's a waste.
What Wendy's talking about could fundamentally change the way we make things. But it's interesting to me that this moonshot, with its far-reaching impact, is essentially behind the scenes. It's software.
It's not as kind of sexy, right? Because we don't suddenly have like this kind of robot turn up and, doing a dance, right? Or doing backflips or something. It's more like we are the tooling and infrastructure behind the scenes that's going to make everything accessible. I think that's going to change, though. It's a little bit like what happened with the 3D printing revolution. Everybody's like, oh, I can basically 3D print this little model, somewhere else around the world. But can you imagine if you could actually do that with any product you want? You could go, do you know what? I want this chair now at home. I love that design. The difference here is you can imagine you could have your own little mini factory at home or your little making unit that would literally download that design. It might even ship you the materials. It'd probably organize it all for you. It gets dropped off maybe by a drone and then just makes it for you.
I love that idea. Never again would I be brought to tears building flat pack furniture. That's the thing about moonshots. They come in many different forms. Sometimes it's big, shiny hardware, and other times It's a powerful tool that empowers others.
It's going to enable more robots to do backflips. That's the thing about it. It's an enabler. It's the same for things like AI for coding. Now Gemini can help you build your code, right? Suddenly applications get a lot quicker to build. It's not just a developer that can do that now. So those types of moonshots are sort of enablers, let's say, enablers of changing fundamentally how whole ecosystems work for humanity.
Everyday Robots and Intrinsic used artificial intelligence to change the game in robotics, showing how learning can replace hundreds of hours of programming to make robots more efficient, more accessible, and much better additions to our lives. And this is just the start of the journey of giving AI a physical body so that robots can help us live well. As robotics moves forward, there are so many considerations about how to ensure they enhance our lives. Someone who thinks deeply about this is James Manica, Google's SVP of Research, Labs, and Technology and Society.
We should be unabashed about having very ambitious moonshot goals on the kinds of things that we want to do to advance society. So we should be incredibly bold. Bold doesn't mean reckless. Bold just means let's be extraordinarily ambitious about the possibilities. At the same time, we need to be responsible. We should be thinking about safety. We should be thinking about making sure these systems perform as intended. We should be thoughtful about the deployment of these technologies and their use, much like we were talking earlier about robotics and AI in the labor markets. Those are all parts of being thoughtful and responsible. So we're trying to solve for both of those two things at the same time. There's a lot of research to be done, lots more problems to be solved. And quite frankly, it's one of the reasons I've always been excited about the idea of moonshots and how do we have incredibly ambitious goals to improve humanity and progress the world.
James is right. With moonshots, we have to aim high and think big. Otherwise, we're just chipping away at the edges, rather than actually creating systems-wide change that can solve the problems we're determined to fix. Here's how Catie Cuan thinks about it.
One of my favorite statistics is how many humans have ever lived and died in the history of our species. It's not that many. It's 100 billion people. 100 billion. So you think about you're 1 in 100 billion. I'm 1 in 100 billion. Okay, let's say I want 10 billion people in the future to use something that I've worked on as a moonshot. It's like 9% of all humans who've ever lived have used something that you've worked. Like saying that kind of stuff at X, not weird. Like totally fine. People here are creative in the classical definition of that word, in that they literally manifest things out of nothing. I think normalizing that on some level is unique.
And that's what we aspire to do here every day. You've been listening to the Moonshot Podcast, a Blanchard House production for X, the Moonshot Factory, with me, Astro Teller. If you've been enjoying the podcast, hit subscribe, drop us a rating, and leave a review wherever you're listening. It'll help more people find us. And if you want to see these moonshots in action, check out our YouTube channel. That's X, the Moonshot Factory on YouTube. Stay with us because we have lots more amazing stories to share with you over the course of this series. And in the next episode, we'll be tackling the hidden problem of what to do with all the stuff the world doesn't want anymore.
We extract trillions of dollars of raw materials from the earth, and then we just throw it all away.
There are 4 times as many calories grown in the world of edible food than we actually eat. So where does all that extra food go? It's like money going in the trash can.
So what if we could actually take that thing that's at the end of its life or use and then use that as a raw material instead of extracting all over again?